Chapter 15, Number 19. A cylindrical container with a cross-sectional area of 65.2 centimeters squared holds a fluid of density 806 kilograms per meter cubed. At the bottom of the container, the pressure is 126 kilopascals. A, what is the depth of fluid? And B, add the pressure at the bottom of the container after an additional amount of this fluid is added to the container, assuming that no fluid spills out of the container. So there's sort of an implicit assumption they've made that we're going to stick with, which is that the container is open to the atmosphere at the top, so that whatever this fluid is at some depth h, we have a pressure at the bottom which is 126 kilopascals, and then we have a pressure at the top which is 101 kilopascals, which is atmospheric pressure, and then we have a fluid inside, something like that. And so we can just fall back sort of on the basic principle that the change in pressure from the top to the bottom is rho g h. Solving that over, we find that h is delta p over rho g, which is 126 kilopascals minus 101 kilopascals, all over 806 kilogram per meter cubed times g, which is 9.81 meters per second square. This is 3.16 meters. And we have 3 sig figs, so that seems about right. Okay. And then part B says if we add an additional some number of cubic meters to this fluid, what happens to the pressure at the bottom? So what we want to do is figure out how much extra height did we add. So let's switch colors. So the change in the volume is the area times the change in the height, which means that the change in the height is the change in the volume over the area. The change in the volume is 2.05 times 10 to the minus 3 cubic meters, and the area we were given was 65.2 square centimeters, and that's kind of annoying because we're in meters, so I'm going to convert this and say that there is 1 meter per 100 centimeters, but then I have to square it because I have this square, and I need to make sure I get rid of the square down here. So we end up with a change in height, which is 0.314 meters extra depth, which will turn into some amount of extra pressure. And delta P here is going to be, call this delta P star. The new delta P, the extra bit we get, is going to be rho g times that height. So if we do all of that, we get 2,482 pascals, which becomes 2.48 kilopascals, and therefore the new pressure, which is going to be the original pressure we had at the bottom before, plus the amount we just gained, is going to be 126 plus 2.48, which is 128.48 kilopascals, but we can't create significance, so we have to round this, and I get 128 kilopascals. The textbook is 129 kilopascals. I'm pretty sure somewhere along the line we just disagreed on rounding for the sig figs. So we end up with that amount.